Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to finish up the second video for our position, velocity, and acceleration graphs. Now this is looking at the whole graph. The last video we did was just the pieces, trying to put the pieces together, and this is the whole, right? So watch that first video, you'll know how the pieces match up. And because of the way those pieces matched up, and because of the things that we said on the last video, the previous video, not this one, okay, we can say these things, okay? So I have marked on here, hopefully it's large enough, 1, 2, 3, 4, 5, 6, 7, 8, 9. Same thing on here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, 10 is just stopped. That really doesn't need to be there. Okay, so as you can see, the numbers correspond to the same thing all through the graphs, which is this, okay? So you should be able, the point of this graph, the point of this video is just to show you how to put these together, but it should be pretty straightforward how to do this, okay? Based off, if we give you this graph, you should be able to make these other two graphs. Either conceptually, right? If you don't have any numbers, you still know what's happening here, so you can still make a slope, right? If you know this is speeding up, you better have a slope in the first part of your graph if there's a slope in the first part of the graph of the displacement graph, right? So these are the things we know. We know that from the last video we had. So if you don't know what that means, you go watch the first video, okay? So we know that. So you should be able to do that, but you should also be able to use the values, right? We can get the rise over run, right, of this graph, right? And get the slope, right, of this graph if we wanted to, and get the actual numbers if we needed to. And for the velocity graph, right, we could get the slope of the velocity graph and get the numbers we need for the acceleration graph. Or we can get the area under the curve for the velocity graph and not get the position, but get the displacement. We'll know how far to draw the line, right? We won't know every data point, but we'll know how far to draw the line because we'll always be given the difference between the final and initial position. That's what that means, right? That's what that means. So the area under the curve doesn't give you exact position. This is a position graph, but you can make your position graph because you know how long the lines are going to be, because when you get the area, that's how long you'll make your line. And so anyway, here we go. So that's what we're trying to talk about there. And then with your acceleration graph, sorry about that, my brain shut down for a second. We can see that just under this graph, we can't do much with the slope. Here we can use slope and area. This one we're just using slope. Here it's just area under the curve, right? Where we can look at where, and again in this graph, you can see that the area are just going to be squares, so it really is this straightforward. But the area under the curve for an acceleration graph is going to be the change in velocity, not instantaneous velocity. Watch the previous video if you don't understand what I'm saying, but change in velocity. So the area under the curve lets you know how long to make these lines, because you know the difference between the final and initial instantaneous velocities, but you're just getting the change in velocity from the area under the curve here. Big thing to point out from this, okay, that isn't made straightforward, that you need to know, this is important, all this stuff's important to write down, but this is super crucial, is that it's clear from this graph that the motion that we're trying to talk about here, okay, is with constant acceleration, okay? That's important because what we do is we actually get this equation right here that I have right here. It's deceiving because you can't see it, and I do it in the kinematics video, I derive it for you. But we actually derive our kinematics equations from these graphs. So we derive our kinematics equations from graphs with constant acceleration because that's the type of motion that we're trying to describe here. So you already know that if your graph, right, if your graphs don't look like this, you can only have exponential curves in your position graph. You can only have just straight slopes or plateaus in your velocity graph, and you can only have plateaus in your acceleration graph. If you have curves in your velocity graph, you're doing something wrong because that means it's a change in acceleration. That's what I'm trying to say. So the shapes in here are indicative that you see in each, right? The curves in here, the mesas you see in here, and the plateaus that we see in here, right, are indicative of constant acceleration, all right? Also, this graph that we have here, I should have put it on here, but this can be our positive x. This over here can be our negative x, and we can call this spot right here our origin point. This is trying to just graph this. I'm going to show you real quick, right? So we're starting at an origin point. which is what that's trying to show us, right? I speed up, rate of constant velocity, stop, turn around, start to speed up again, cross my origin point, stop, turn around, start to speed up, slow down again, and come back to my origin spot. That is all this graph is, right? I speed up away from my origin point, I slow down, stop, turn around, start to move towards my origin point, cross my origin point, start to move, slow down, turn around, and then move back towards my origin point and stop, right? Which is exactly what I did. I moved away from origin point, stopped, turned around, crossed it, stopped, turned around, and came back, right? And that's what this is showing us. That's what this is a graph of. So the first thing I did, I was speeding up, right, in the positive x direction. And that's what this is showing us. So on the position graph, that will look like this. On a velocity graph, it'll look like this. This will match. But both of those things right here, not so much for acceleration. We know because the acceleration graph is from this, but both of these positions, you can say all this stuff. Okay, you know you're doing this thing. For the velocity, maybe not so much away from origin. This stuff, this information right here is probably specific to your position graph. But everything else besides this away towards origin thing that we have here, anything besides this you can say all of this on this graph. Because of what we said on the last video, we have a bunch of science that if we know one thing, we know the other things. If we know instantaneous velocity matches our position sign, or the direction that we're moving, right, or displacement sign. We know if we're speeding up, acceleration and net force will match our instantaneous velocity sign, where if we're slowing down, acceleration and net force will be the opposite sign of instantaneous velocity. Not change in velocity, instantaneous velocity. Go watch the previous video. If you don't know what I'm talking about, you're missing a lot without watching that other video first, okay? So, the first one we know we're speeding up. Positive x direction, positive velocity, right, and positive acceleration. So we have that point. Let's say that was all we were given. So you would just draw a line like this, whoop, and that would match that point right there that we're talking about, right, that exponential curve, right? And then once this starts to go to a straight slope, we're reaching a constant velocity. We're still moving in the positive x, right? That's just me still moving this way, right, away from origin, right, away from origin. But no acceleration, it's constant velocity. The speed's constant, no change in motion, okay? So the acceleration will be 0. And again, for this, we'll just write a plateau, and we saw from the last video that plateaus on here mean 0 acceleration, right? It's like plateaus on here mean stop, plateaus on here mean 0 acceleration or constant velocity, and that's what this is saying. So again, everything that we're saying here for 2 can be said for both 2's. What you should see and what you should study from this video that we can't really go through as I talk here, because that's something that you're going to have to do that takes a lot of time, is compare these videos and see where things are different, right? Like I have stop turnaround position here, where stop turnaround position on this graph is in a different point. So there's a lot of things for you to go back and look at after you have not just watched this video, but copied these graphs down, written all this down, matched them all up, and seen the difference. You have to do all that work. Watching just a video of physics doesn't help you. If you don't do the work with it, if you're not writing this stuff down, it's not gonna help you a bit, okay? Just watching physics is the worst thing you could do. All right, there's a saying in physics, it's easy to watch someone come up with the logic, it's hard to come up with it on your own. So if you don't practice it, you can't come up with it on your own. All right, so we know at 3, right, we're starting to slow down, right? We're approaching a plateau. Plateaus mean stop, so if we're approaching one, we're slowing down, but we're still moving in the positive x, which are an instantaneous velocity, still positive, but our acceleration will be opposite because we're slowing down. Again, we know this because we know the relationship between acceleration and instantaneous velocity, right? And then once we have that curve, right, or we might have been given this whole curve, we would want to draw that, and then 3 will be represented by that slope right there, right? Okay, and then 4. Right? We start to speed up, right? We're moving away from the plateau, right? So we start to speed up, but now in the negative x direction. So we have stopped and turned around, right? I'm over here right now. I've stopped and turned around. I'm headed back this way, right? So look where that is here. That's right here on the velocity graph, but it's right here on the position graph. If you don't know why, go watch the previous video. Yes, and you're going to hear me say that a lot because in the previous video we described all that. I don't need to describe it again, okay? So go watch the previous video. You'll know why these are true. You know why this is the stop turnaround point here and why this is a stop turn around point there, okay? It's important that you understand that. We stop, turn around, and we start to speed up again in the opposite direction since we turned around, right? And so we're moving in the negative x. If we're moving the positive x and we turned around, we got to be moving the negative x now. And acceleration, since we're speeding up, will match instantaneous velocity. And now we're moving towards origin, right? We're moving away from it, now we're moving towards it, because this line is origin, and like I just said, it's really just me walking back this way towards origin, right? Okay. I'm speeding up, right? And that'll be indicated, right, by this right here. So we stopped and turned around, but and then we started to speed up in the opposite direction. We know slopes on this mean speed up or slow down, right? We know when we're moving away from zero velocity, that means speeding up. Go watch the previous video if you don't know what that means. So we're speeding up, and the negative x, we know that tells us, that right there, we know that tells us all that. Just because of what we know all this, right? If we're down here in the negative, right? So just having that slope down there tells us we're moving in the negative x direction, okay? And then, right, what happens is that we cross origin, but what do we do that at a constant velocity, right? So I have 5 broken up into A and B here, but 5 really isn't A and B over here, it's just 5, but it's still representing the same thing, okay? I just want you to see that for 5A, we're moving at, right, constant speed in the negative x direction towards origin, but then we cross origin right there, right? We can't really see it over here. I'm assuming, crossing origin would be somewhere right there, but we really can't tell so much, unless we got really detailed with this graph. So we're just gonna say, right, for A, we were headed towards origin, then B, we're headed away from origin, but we're moving at a constant speed. It just looks like this, right? That's moving towards origin, then moving away from origin at a constant speed. We're moving at a constant velocity towards origin, now away from origin. That's all that means, very simple motion, right? Okay, and then again, now we're moving away from origin, but still in the negative x and negative velocity. Acceleration 0, because speed is constant. That's what a straight slope means on here. And so that's what we're trying to say here with 5, right? Is that constant velocity, just the plateau, and 5 is all being represented, negative x direction, negative velocity, acceleration 0. That's what that means there, okay? For 6, right here, right? Approaching a plateau, which means we're gonna stop, because we know plateaus on a position graph means stop. So we're slowing down, still moving in the negative x direction, so our instantaneous velocity is still negative, but acceleration is positive because it's gonna be opposite. Our rate of change in motion is opposite of our motion when we're slowing down, right? But still moving away from origin, right? And so that's gonna be this, right here, we're slowing down, and so 6 right here means we're approaching zero velocity. Zero velocity means stop, so we're approaching it. And that's what 6 means, okay? And again, this is over here too, 6, right? We said that acceleration should be positive, but we see right here, acceleration is positive. That's about all you can do with this. That's why I'm not really relating it, but I want you to say, hey, he said acceleration was negative at 4. Better be negative at 4, and look at it is. Okay, so that's what we're saying, okay? Make sure that you can just make that graph off of these, because there's not much you can do. All right, and then, so that was 6. So now 7, right? Now we're speeding up towards origin, which means now I'm over here starting to walk towards origin, speeding up, right? That's what 7 is trying to tell us. So now I'm moving, I stopped and turned around, so now I'm moving back in the positive x direction. So even though I'm over here, I'm facing the positive x direction, so that means I'm moving the positive x. When I'm over here, but I'm facing that way, just because I'm standing near the positive x doesn't mean I'm on the positive x side. It's the direction I'm facing. These are vectors. So if I'm facing this way, if I'm facing the negative x direction, that means I'm moving the negative x. Doesn't mean what I'm near. It's the direction you're facing. These are all vectors. Their signs have to do with their direction, not being above or below 0, right? Their direction only. So 7, speeding up, which that's what that means in the positive x, right? We're increasing speed, moving from 0 velocity or stopped. So that's what that means. And then we know we're coming towards origin. We reach a constant velocity, right, at 8, which is going to be a plateau on a velocity graph. Okay, but we're still moving the positive x, positive v. Constant speed, which means no acceleration, no rate of change in motion. And then 9, we're slowing down. I'm moving through this faster now because I'm sure you're getting it, but all the information's on the board anyway. 9, we're slowing down, which means we better be approaching 0. Right, but we're still moving in the positive x, positive v, right? It's me just approaching 0 and then stopping here. That's where I stop, right? So that's stop position there. Right? So that's what's going on there. But again, 9 is here, 9 is here. So it's your job to match these up, because as you can see, this has more humps than this one, right? 9 is on this side versus this side. So that's for your job. That's your job to go watch the 2 videos and answer the questions why these look so different. You have to know why for the test. If you don't know why these are different, you can't understand, this isn't going to help you, all right? So the next thing we want to do is make sure you can get the area under the curve, okay? And the slopes of things, all right? That's important too, all right? So let's say that we wanted to get how far we went after 5 seconds, right? Well, first we know the area under the curve is equal to the displacement, right? And the only area, since this is the most complicated shape you can have on a velocity graph right now, is you can either break this up into right triangles or squares. So the only areas that you really need are the areas for a square, which is base. This is the base. This is the height. So base times height, the number of the base, the number of the height, or 1/2 base times height for a triangle. Okay, but the base and the height are the same for both of these. That's why I use those so that it matches. Okay, so using those, we can find out what's going on. Okay, so after the first 5 seconds, I totally see what I did here. To do this, there we go. Right, we see that after the first 5 seconds, there's a triangle, right? A right triangle, right? So it's 1/2 base times height. If I want to know how far I went, it's just the area of that right triangle right there, right? Because we know the area is the area under the curve is the displacement. So I start with 1/2 base times height, and I know my base is 5, because that's 5 seconds, so that's the number 5, right? And I know that the height is 10 meters, at 10 meters per second, or just 10, right? So 5 times 10 is 50, but then it's also multiplied by 1/2, or we divide that number by 2, so 50 divided by 2 is 25. So I went 25 meters, right? Now I don't know the exact thing, but I know that how long to make this, right? These are all going to have numbers, and I'm going to draw, right, this in terms of that first part, right? I'm just describing me speeding up. So, right, this would, somewhere around here, would be 25 meters. We know the number there because we got the area under the curve, and we know that's where it stops to, right? That's where it becomes a straight slope. So that is where we stop speeding up. That is only describing the part where we're speeding up. So we went 25 meters right there, and that's how we kind of get those values in these graphs, okay? So that's the area, right? If we need the slope, right? If we want to know the acceleration, right? Then it's just a rise over run, right? Where that would be 10 over 5, which is equal to 2. So that's 2 meters per second squared. Remember, the acceleration is equal to the slope. So we can also get that number. So this part right here, right? We went 25 meters because we got the area under the curve, right? And we know, right, that the acceleration was 2 meters per second. So we can make that, and then we can use that number, right, and get the area under the curve of this, right, to get the numbers over here if we need it. But we see they match, right? We said that after having 2 meters of, or acceleration of 2 meters per second squared for 5 seconds, we should be moving at 10 meters per second, and that's what this says, right? We're moving at 10 meters per second after 5 seconds. So see how these correlate? That's how you have to be able to do this, okay? But let's just do another one. Let's say after 10 seconds. I'm not going to do all that, right? Because I did a lot. Here we did both displacement. So this is after 5 seconds. We know we moved 25 meters. And after 5 seconds, we know what our acceleration is. Okay, so that's how you start to put numbers on these graphs. Okay, that's how that works. So you have to have numbers from one of these graphs to do the others. Let's say after 10 seconds, right? 10 seconds is a square and a triangle. So we know that the displacement is going to be the base times height plus 1/2 base times height, both of these, right? The base times height for the first one, right, is 5 and 10, right? So 5 times 10, oh, I'm sorry, it's over here, 5 times 10 times 1/2, because that's a triangle, right? Based on 1/2 base times height, because that's a triangle, so we want the area of a triangle, against the base is 5, because that's 5 seconds, and the height is 10. And then here, right, for the second half, for the square, it's just base times height, right? Not the 1/2 base times height, just base times height. That's still just 5 times 10, right? Because from 5 seconds to 10 seconds, that's just a 5 value, but we're still at 10 meters per second, right? So that becomes 5 times 10. So we got 5 times 10 is 50, and 5 times 10 divided by 1/2 is 25, which we saw over here, right? So we want to add those together and we get 75 meters. So after 10 seconds, we see that we move 75 meters, right? Or we can say, right before we start to slow down, right here, we can throw it on there if we want to, that's going to be what? 75 meters. We know we move 75 meters right before we start to slow down, right? Does that make sense? So we can see how far we moved right there just from that, right? We moved 50 meters. So that's how this works, okay? So make sure you use both videos and go back and forth and understand what I just did. It's super crucial, okay, that you understand that you're able to match up all these numbers, do all these numbers, and put the areas and the slopes and everything in terms of the numbers into these graphs, okay? Hope this was helpful, and I'll see you on the next video.